right, let's implement this part together. What we need to do is first create a layer. And we're going to pass the same parameters because we use the same parameters for all the RNN state, even though we have different time steps. That's the beauty of RNN. In itself, H is going to be layer dot forward XS, the teeth input, and self H. So this one updates our H like this. And we store all the H's and append layer here and return H's like this. And how do you calculate the backward gradients? First, we retrieve parameters like this. So we retrieve necessary hyperparameters like this. First, initialize this as empty array like this. H initialize as 0, grades 0, 0, 0 like this. And for T in reversed, because we are calculating loss from backward. And in the class slides, I mentioned that H1 gets affected by L1, L2, all the way to LT. And H3, 4 gets affected by L4, L5, and all the way to LT, like this. So we need to calculate variance from back. And this layer gets affected by these layers. And what we are going to do is, from backward, we are going to accumulate gradients and pass those accumulated gradients to the previous time steps. So here, we first retrieve the layer at the current step and calculate backward gradient by passing dh as at times the t. And here, we need to add dh from the past time step. Okay? So, to go from H4 to H1, we need gradients from H4, H3, and H2. And that's why here we're adding the gradient from the previous time step. And this one becomes a new gradient. Because we are going to store the dx as like this, and this part might look tricky, however, don't worry. For I broad, enumerate layer dot grad. So this layer contains gradients in respect of Wx, Wh, B. And what we are doing is accumulating the gradients. Okay, so this is to accumulate gradients for Wx, Wh, and B. This is backpropagation through time. And after we accumulate all the gradients, what we are doing is set the gradients of the internal states is the accumulated gradient. Self dh becomes dh, and we return dxs. Okay, so this is backpropagation through time. And sometimes, so basically time RNN is an interface for using this RNN class more efficiently. So you can view this as an interface. And because this is an interface, you sometimes want to set state specifically. Maybe state from previous one-to-many or many-to-one RNN. Or you can use this for many-to-many or connecting many-to-many to many-to-many RNN architecture. Anyway, for various reasons, you want to set H as you want. And sometimes you want to reset the state. In that case, H becomes none again. All right, that was time RNN. And what we need more to implement language models is time embedding. So rather than receiving just one instance, it's going to receive multiple instances. And this one makes implementing language models much easier. And we're going to implement time affine as well. And they basically follow similar architecture as time RNN. You can compare the relationship between RNN and time RNN. Then it might be clearer, it might become clearer how to implement time embedding and time affine. And we're going to also implement, so this one should, time embedding should receive parameter W, XS, D out, time affine should receive W and B, XS, and D out like this. And time soft mix with loss. This one doesn't need to receive any parameters, but it receives the data and the ground truth label like this. Okay, so we've implemented embedding, affine, and softmax with loss. And you can compare the relationship between RNN and time RNN and try to implement these three classes. Okay, these are our next KPP exercise.